Okay, so finally I've started the recording for the fifth unit since many students wanted some extra material. So this is just another perspective compared to what has already been done in imparters and during the online classes. And you can use this along with that material also. Okay, so unit 5, mainly there are two topics. The first and the biggest one is the one about combinational circuit design, where we will be discussing various techniques to improve the speed of static CMOS circuits and some other logic families itself. That is, different types of designing circuits. Every circuit may not necessarily have pull up network, pull down network, and all that. So, that is all going to come under the first part of the unit. The second part, and a much smaller part, is about what is called as sequencing. So, our modern digital systems, they are divided into different blocks, and the operation is connected. Not the operation, but the blocks are connected through registers, and whenever we have a register, we know that there should be a clock signal. So how to design the circuits and all that is what we will discuss in the second part. Okay, so let us look at the first part, what we are going to talk about. We will start with the static CMOS family itself. So what we have been designing so far, all the gates, NAND gate, NOR gate, etc., that you have seen are belong to a particular class of circuits, a particular family of circuits called as static CMOS circuits. So in static CMOS circuits, there is a rule. There will be a pull-up network consisting of a few transistors. There will be a pull-down network consisting of a few transistors. Further, in the pull-up network, there will be only PMOS transistors. In the pull-down network, there will be only NMOS transistors. And inputs are given to both the pull-up network and the pull-down networks. For example, if there is an input A, NAND gate or NOT gate, the input A is given to NMOS network and the PMOS network. And the number of transistors is approximately 2n, which is n is the number of inputs. And this is by far the most popular, okay, class of CMOS circuits. So we're looking only at CMOS families. Okay, we're not going to look at any other families. We're not going to look at BJT, etc. But with CMOS itself, there are many families. So the first and most important, which we have seen over the last few units, is called as static CMOS circuits. And when it becomes a little difficult to go beyond a certain speed limit, okay, so suppose there is some particular path in my design, and this is forming the critical path. So when you are generating that timing report, right, there are some gates which are part of that timing report. Suppose the timing report is, say, 700 picoseconds, and it is the best you can do with static CMOS circuits, but unfortunately the requirement is 600 picoseconds. But we have got the best circuit, we have done everything we can from our side. Then we have an option of getting one extra level of improvement if we change the static CMOS. Suppose in your circuit there is a NAND gate somewhere that is part of the critical path. The NAND gate can be replaced by another NAND gate, but belonging to a different logic family called as dynamic CMOS family. And we will look at this, of course, in much more detail. But it's a little more complicated than static CMOS because there are different phases of operation. There is a pre-charge phase and a evaluate phase, and there are some rules also with respect to the inputs and outputs. But the most important reason why anybody uses dynamic CMOS family is they have a larger speed, they have a better speed compared to static CMOS family. So if you want to really speed up an adder, for example, you might have seen this circuit called as a Manchester carry chain. A Manchester carry chain is example of a dynamic CMOS circuit, and it is CMOS carry chain circuit. So that is the whole idea of the dynamic CMOS family. And finally, we have one more family, which is sort of historical. The static and dynamic you will find in all practical circuits. If you take any circuit, maybe around 98% of the gates will belong to static CMOS, and maybe around 2% will be dynamic. Okay, there will be 0% ratioed, and the reason for that is this is largely historic. It is sort of a part of the evolution, and it also helps us in understanding dynamic CMOS easily. So we will not go too much into ratioed logic. We will see some gates, but purely from a historical perspective. Today, no practical circuits are there in ratioed logic family. So the first part of the unit, we are going to see only static CMOS circuits, okay? But we are going to see different ways in which we can reduce the delay. So we have a gate, okay? It's made of static CMOS family only. But given that, how can we improve its speed? And we are going to see a few methods called as bubble pushing. We are going to see some more methods called as input ordering effect. We are going to see some more methods called as skewed gates, etc. These are all still static CMOS family itself. Okay? But within that family itself, how can we improve the speed? So that is what we are going to see in the next few slides. So we will start with the first approach called as bubble pushing. And this is a very simple approach, mainly based on the idea that in CMOS circuits, we know by now that the circuits are naturally inverting, that is static CMOS circuits, right? Whenever we put transistors in series and parallel, we don't actually get F directly, we get F bar. So if I want F, I have to add an inverter at the output. So what that tells us is, if it is possible, okay, instead of using AND and OR, you change them into NAND and NOR. So obviously we cannot change the function itself. So the thing to do is try to change your implementation in order to have more amounts of NAND NOR gates compared to AND OR gates, because AND OR gates have more area and delay because of the extra inverter at the output. So that is the idea of bubble pushing. How to do it is very simple. Okay, so the first step, it says basically what you have to do is add two inverters at the output. So anywhere in your circuit, for example, if you have a AND gate or OR gate, okay, we cannot change the function. So we cannot change the functionality of the circuit. That function F is fixed, what you see here, right? So in this case, let us look at this example, how the bubble pushing will help us. So let's say that we want to implement the function F equal to AB plus CD. So here I'm generating AB term, here I'm generating CD term. This is the plus OR gate. And this design is not very nice from a bubble pushing perspective because it is full of AND gates and OR gates. We don't want any of these three gates. I want only NAND NOR. So what I do is at the output of each of these three gates, okay, I add two inverters. I add one inverter here and I add one more inverter here. We know that theoretically it doesn't change anything in the circuit in terms of the signal values, because any signal, if you invert it twice, you get back the original signal. So because of that, we can do that without changing the function F. So that is what they have done in this step. They have taken the gate, AND gate. This is the first inverter that is attached to the AND gate itself. The second inverter is here, okay, and that comes here. And they have done that to this OR gate also. Added one inverter here, one inverter here. So total of 6 inverters have been added, 2 for each gate. So 2 inverters here, 2 inverters here, 2 inverters here. Now what you do is you take the AND gate or OR gate, whichever you have, okay, and the first inverter, you attach it with the AND gate or the OR gate. So that will change automatically from AND to NAND or OR to NOR. And that is what has happened here. Here, here, and here. The AND gate has eaten up the inverter, but it has become a simpler gate because NAND is the one that we can directly implement. Similarly, here also NOR is the one that we can directly implement. So that is the first thing. What do you do with the second inverter? The second inverter, you push it to the next stage. Okay, that is, you give the inverted inputs. And what inverted inputs does, from De Morgan's laws, okay, if I have a AND gate and instead of A B I give A bar B bar, the output of the AND gate is A bar into B bar. What is A bar into B bar? It is nothing but A plus B the whole bar. So AND gate will get converted into a NOR gate, and gate with inverted inputs gets converted to a NAND gate, and that is what you see here. Okay, so we have the NAND gates here with and this thing has combined with each other, and in the output of this, okay, we have a two inputs that are coming here. These two inputs together with this OR gate make this also a NAND gate. So that is what you see here. The OR with the inverted inputs is actually a NAND gate. So the end, we have implemented F equal to AB plus CD without any NAND nor AND OR gates. We have one NAND gate, another NAND gate, and this is also a NAND gate. And that is the idea of bubble pushing. Start with any AND OR gate in your circuit. Okay, add two inverters at the output. The first inverter you take it with the gate itself and you convert AND OR to NAND OR. The second inverter, push it to the next stage, and using De Morgan's laws, any gate with inverted inputs we can transform in this way, AND OR to NOR or NAND. And in this way, as many gates as possible, we will try to convert from AND OR into NAND NOR. So one exercise that you can try, create a 6 input OR gate. Okay, so we cannot directly create 6 input OR gate. Generally you will try to create it using 3 input gates and 2 input gates, and the requirement or the constraint is you're only allowed to use NAND and NOR. You're not allowed to use AND OR gate. So this is an exercise that you can try where this method of bubble pushing can be used. Okay. So the next topic, again, we are still in static CMOS only, but this is a different type of gate which is called as a compound gate. So we have the basic gates, which is our inverter, NAND, NOR, AND, OR, etc. And this is a slight modification of that. It is called as a compound gate because it can implement different types of functions. And generally, there are two types of these compound gates. The first one is called as this AND or invert or AOI. And if your function that you're trying to implement is in product of sum form, that is product of sums. There are many sums, and you want to find the product of all those, then you have a AND or and invert. Maybe I wrote this upside down. I'll change that. Here, this is SOP, a sum of product. So you first do the and then you do the or, and this becomes product of sum form. Okay, and this basically is a very important class in our standard cell library. If you remember the write HDL function, output, if you have seen that, you would have seen that many AOI, OAI gates will be there. And this is because they occur very commonly in uh, standard cell libraries, and they occur very commonly in digital implementations itself. You will never see a netlist with only NAND NOR. It's just too simple. Always there will be some AOI and OAI gates. Okay, so let us see what is there, how we design gates in these families. So let us look at the first of these gates, and already we see some complications. So we'll go through its each by. First question is the implementation, and generally these, like static CMOS, this is also a static CMOS family itself. It's just a type of gate. Like NAND gate belongs to static CMOS. Compound gate also belong to static CMOS. So just like any static CMOS gate, the first thing is the functions are naturally inverting. So you see that automatically we can implement the function only with the complement on top. If I want the non-inverted function, I have to add a inverter. So let us look at one of these functions, y equal to a into b plus c. So this is in sum of product. So this is one product term. This is a single term, and we have to add those. So it becomes a AOI gate, and this is what the gate looks like in the gate level schematic. But in the circuit level schematic, you see that we don't have to have a separate AND gate and a OR gate. We can implement using a single compound gate. This is the main advantage of compound gates. We don't need to implement the AND, take the output of that, take another OR gate, and then implement the function. We can directly use this single structure to implement the whole function. And the way to implement is very simple. A, B, this is in AND it, so it is in series, plus C, plus C. And once you get the pull down network, the opposite of that becomes the pull up network, and this is the gate. Okay, so that is the first part of the gate. Now the second question is, how do you get the transistor sizes? That is also very similar to static CMOS design. We want the top part, all of them together, it should be 2. Bottom part, all of them together, it should be 1. So I want this branch to be 1, I want this branch to be 1. How do I do that? This directly I put the 1 here. If I put 1 1, I will not be able to get 1 for both of them in series, so I have to put 2 2. Same thing here, since I want a total of 2, I put 4 4, which is 4 4 4. And if you evaluate this pull up network, it will be equal to 2, which is unit inverter PMOS size, and this bottom will be 1, which is unit inverter NMOS size. Okay, now the question of logical effort comes into the picture. So logical effort, okay, in this case, let us take an example of the input C. Okay, what is the input capacitance of input C? If you see input C in the circuit here, input C is given to this PMOS transistor and this NMOS transistor, the same wire. Okay, so the total input capacitance of input C is 4 plus 1 equal to 5. And that is where we start seeing a difference between compound gates and simple NAR gates. In compound gates, the logical effort can depend upon which input that you are seeing. So in this case, GC, okay, I'll write a GC equal to 5 by 3. Okay, why 5 by 3? Because the equivalent inverter is 2 and 1 3. But GA is not 5 by 3 because the input A is connected to one PMOS of size 4, one NMOS of size 2. So GA is 6 by 3, and similarly this is also equal to GB, and that is where the compound gates are slightly different compared to static CMOS gates. And NAND gates, since they are usually connected to one PMOS and one NMOS and all the circuits are a little simpler, you will have only one number for logical effort. If it's 2 input, one number. If it's 3 input, another number. But when you're talking about these gates, we have to see, okay, what is the input capacitance, and that should be divided by a equivalent inverter, and that is why we see the different numbers for different inputs. So GA, GB, GC. So let us you can try to do this for a NAND and NOR, etc. Let us try to do it for a much bigger complex compound gate. Okay, so a double level of complexity. So let us look at the gate before we look at the sizing. Okay, so here is the gate and AB plus CD. So look at just one more example and we'll explain this example. So again, same AOI because it is a sum of products. So first the product is that is why and. Okay, after the and you can do the or. So and or then invert. And here instead of AB plus C, you have AB plus CD. So two terms. And again, we don't need AND gates and OR gates. We can implement this whole function. It's a single structure, and the sizing again similar to the previous argument. This whole top part should be equal to 2. This whole bottom part should be equal to 1. And in this case, okay, because it's somewhat symmetric, GA equal to GB equal to GC equal to GD equal to Okay, because all the input capacitance of all the inputs are the same. It is 4 plus 2 equal to 6, equal to 6 by 3. So it's much simpler in this case. So let us look at this complex AOI. So the first question is, we need to get the sizes. We don't even have the circuit. So we need to get the circuit and we need to get the sizes for this function. So A into B plus C plus D into E. So the function is first we have to do the product terms. Once we have this product term and this product term ready, then you can do a sum. So it is a sum of products or a AOI gate. So it's basically going to have two branches. In one branch it will be A into B plus C, and in the other branch it will be D into E. So I will switch to the whiteboard. So I think it is A into B plus C plus DE. So I'll just write that here. A into B plus C. This is one product term plus D into E. Okay, so then we can first draw the gate. So we have on one side A into B plus C. So that will come as B plus C here. And then on the other side is just D into E. So two transistors in series. And then bottom goes to ground. So we'll name all the inputs also. So just there's no confusion. This is input A. And then this is B. This is C. And here is D and E. And this will be the output, and exactly opposite of this will be the pull-up network. So these two will be a parallel in the pull-down network. They will be in series. So I will have DE in parallel because they're in series in the pull-down network. And in series with that, I will have on one side A, and the whole thing is B, E, and these are all PMOS transistors. So there should be a bubble. There also there should be a bubble. So this is B, E, and then this is A, this is B, C. Okay, so finally the circuit is ready. This is a complex AOI gate, and Once this is ready, now we can give the sizes, and always the whole thing should be equal to 2. Whole thing should be equal to 1. So let's start with the bottom. So this would be 2, this would be 2. So that r by 2 plus r by 2 will equal r. Here also this will be 2, and this also will be 2, 2. So any one branch, even if it is conducting, in the worst case 2 and 2 will give me 1. And this is the pull down network. Pull up network will start with the top. Okay, so I have this plus this together should be size of 2, and which means that this will become 4, 4. Okay, this will become 4 just like that, and these two will become 8, 8. So that together they become 4, and this is the sizing for all the transistors. So now we can write the logical effort. GA equal to, find input A. Here is 4, here is 2, 6. It's all equal to, equivalent inverter is 2 and 1, so 6 by 3. GB, find input B. Wherever the input is, see the transistors 2 and 8. So suddenly we see very high number for GB. So 10 by 3. And C is also the same. So GB equal to GC. 10 by 3. And similarly D and D are the same. GD equal to GE equal to 4 plus 2. 4 plus 2, both are the same, which is also equal to 6 by 3. So this is the logical effort for a complex gate, AOI or OAI, and this can be different for the inputs because it's not symmetric like a NAND gate, NOR gate. Some branches have more transistors, some branches have less. So in the end, since we want the 2 1 for the whole networks, we have to size them accordingly, and then for each input we see. So if you want to ask what is the logical effort of this gate, if I want one number, then you have to mention the worst case, that is 10 by 3. Okay, so this is about compound gates. The whole idea is this whole function, right? We are implemented f equal to. We don't have to implement this as a separate AND gate or OR gate and one more OR gate. We can implement all this in one single stage of logic. So that is the idea behind compound gates. How do we make it faster? We make it faster by implementing all of them as a one single stage. Even though the stage might be quite complicated, it might be cheaper than an ordinary function. So that is about compound gates. So let's go back. Go back to the slides. Okay, and this is a nice exercise. Now you can try this now that you know about compound gates. You implement f equal to ab plus cd using your bubble pushing output. Bubble pushing, we saw the output for ab plus cd. I use this circuit for ab plus cd. Okay, and another circuit use this ab plus cd along with the inverter. This is not ab plus cd, this is ab plus cd the whole bar. So implement this ab plus cd function in two ways. One, using the 3 NAND gates result of bubble pushing. There also there's two stages of logic. The other implementation using AOI gate, here this one AOI 22 along with one inverter. There also there is two stages of logic. Now that you have all the values of input capacitance, output capacitance, we have the beautiful method of logical effort. Apply the method, get the sizes for all of these transistors. Okay, and then we can verify. This is the idea behind two different implementations. How we can get the best option. We have two options and giving the sizes, and we can check which delay is slower. We will go with that particular design. So this is solved in the book. You can go through it. It's in page 330. Okay, so another way in which we can make our gates faster This is again, we are still in static CMOS only. We have not changed our logic family yet, but we have some methods by which a NAND gate, NOR gate itself will operate a little faster. And that is by something called as input ordering. Okay, so in general, in our, for example, when we're doing the NAND gate, NOR gate in the lab, right, the input was coming from a V pulse, and that's because we have a very simple circuit. But in most practical situations, the inputs A, B, etc., they'll not come from a pulse is only available at the primary output, a primary input. Somewhere deep inside the circuit, the inputs are coming from other gates. So then what will happen there is, in V pulse, you were giving all the inputs. Many times you would have seen they're changing at the same time, right? I mean, one input is changing at 5 nanoseconds, other input is also changing at 5 nanoseconds. But that has almost probability zero of happening in real circuits, because even as you know, suppose my input A is supplied from a NAND gate, input B is supplied by an inverter. I know that inverter is faster than an AND gate, right? So I will get the input faster at the inverter than at the NAND gate. So that is why we have a particular method in which we can make the gates a little faster. So the question that we're asking here is mentioned here. Okay, can we make our gates faster? Okay, if we know in what order the inputs will arrive. So you just the situation we discussed: NAND gate and inverter. NAND gate is always faster than inverter is always faster than NAND gate. That connection can never change because CMOS circuits don't have that sort of flexibility. So which means that every time the output is coming from the inverter connection, that signal is always going to change first. Okay, and then after a few picoseconds, okay, then the NAND gate signal will change. So that is why there is a difference in the arrival time. So using that, is it possible to make our NAND gate or NOR gate a little faster? And answer is yes. Okay. What is the simple idea? The simple idea you see in this example here. Okay. The pull down network, there is the output node Y, and then there is a intermediate node X. Okay. Hold on 1 second. Oh, sorry. So this intermediate node, okay, also needs to get charged or discharged based on the operation. And that is where this whole input ordering comes into the picture. Suppose the output node only has to be discharged, then it's going to happen fast. If the input output node Y and this intermediate node X have to be discharged, then it's going to be a little bit slower. And that is what we're trying to solve with this ordering this thing. Wouldn't it be nice if the B first came, that is B first went from 0 to 1. Okay, so this transistor is conducting and this node X gets discharged, and after a few picoseconds A has arrived and this intermediate node is already discharged. There's no issue of anything from X, only the node Y has to discharge, and that can happen a little bit faster. And that is what we are aiming to get here by way of a rule. Okay, what is the rule? And for that we need a few definitions. We already have defined early inputs and late inputs. Whichever signal changes first, they are called as the early inputs. Whichever signal changes last, okay, they are called as the late inputs. So now the question is, how do we, based on this knowledge of intermediate nodes discharging first, etc., how can I come up with a rule for deciding which inputs are the should be the early inputs, which input should be the late inputs. For that, we have another definition called outer input and inner input. Outer now represents the outer part of the circuit, that is transistors which are closer to VDD or ground, because in static CMOS the middle of the circuit is always the output node, and on top is the VDD, bottom is the ground. So opposite of that definition is inner inputs, and these are inputs that are connected towards the center of the circuit. So the input ordering delay effect, the rule to remember is that the outer inputs should be connected to earlier arriving signals. That is what we see here. B is an example of an outer input because it is connected in the outer part of the circuit. It's closer to ground, okay, compared to A. Not that it's closer to ground in general, it's closer to ground compared to A. So the outer input should be such that the signal arriving early. So for example, in this case, this gate will be optimized better if B is the early input. So B input comes, okay, and then it discharges this node, and this node has already reached the perfect value 0. So when A input comes, then only the Y node has to be discharged. So that is the rule that we have formulated. Outer inputs should be connected to earlier arriving signals. Why? So that they can discharge the internal nodes, keep everything ready. Okay, only the output has to change, that is the output node Y, and the later arriving inputs, okay, most of the work is already done, they only discharge the output node value. Hence these nodes should be connected nearer to output the inner. So that is why this signal A, which arrives later, okay, can be connected towards the middle of the circuit, or it should be connected to the inner input, and when this comes, then this is already at final value, only the Y has to be discharged. So this is the rule to remember as the first part. Outer inputs should be connected to the earlier arriving signals, and this, if we remember, we can try to optimize the circuit performance without changing the actual circuit. So one question that you can try, let's take a 3-input NOR gate, okay, and they are given 3 inputs and we'll call them ABC. But I also know from my experience of the blocks generating the ABC signals, okay, the signal C will be generated first. So the first arriving input is signal C. The signal A is going to come next, and finally signal B will be the last to arrive. So this is fixed, right? Because the groups or the blocks that are supplying or generating C, A, and B are fixed. It will never be interchanged. So this is always going to be the order in which they arrive. Now what you have to tell me is you have to draw the 3-input NOR gate, and you have to mark which is input A, which is input B, which is input C, and your delay should be optimized based on this information here. So what is the rule to remember? This is the rule to remember. If you remember and understand this rule, you can design this gate, 3-input NOR gate, for optimized performance. So this is another way in which our static CMOS circuits itself can be made faster through the input ordering rule. So we look at another method. So first we looked at bubble pushing, then we looked at this input ordering. One more method in which we can improve our static CMOS gate performance is by designing something called as skewed gate. So why it is called skewed? Skewed generally means it is sort of a tilted. Okay, here what we are doing is we are going to improve the performance in one transition at the cost of another transition. Nothing is free. Okay, you can never say that I have improved the performance of the gate overall. You can improve it, but at the cost of something else. So typically, if you want to improve the speed of a gate, we can increase the W by L. But increasing W by L means that the gate is going to occupy more area. So whatever you have improved in the speed didn't come free. It came at the cost of higher area. So here also we're not going to get some magic this time. We're going to get some improvement in the performance, but it is the cost of the other transitions. Generally, we know that all our digital gates, we have two transitions, 0 to 1 and 1 to 0. and in certain special cases. So the skewed gates cannot be done for all circuits. It can be done only in certain special cases. So in certain special cases, and the best example is a reset signal. Okay, so reset signal in typical operation, you shouldn't keep getting a reset signal like a clock signal. It should come only when there is some sort of an emergency. Like suppose in your CPU, for example, there is a temperature sensor. If that temperature sensor goes above say 60 degrees, then automatically the computer should shut off, because that temperature can be dangerous. It can permanently damage the circuits. So in that case, they might generate a reset signal. But suppose if you generate the reset signal and it takes about say 3 minutes for the computer to shut down, then it could be really bad. So reset signal is a typical case of an emergency this thing. So whenever you see a reset signal, you should act very fast. So that is why it is very important to generate the signal also quickly. But on the other hand, once the signal has been generated and some action has been taken, okay, then for the signal to go from 1 to 0 doesn't have to be so fast, because the the action has already been taken. The system has been saved. We are not going to burn the CPU. So then it can slowly transition back from 1 to 0. So this is a typical example of a skewed gate. Suppose some inverter, some NAND gate is responsible for generating this signal. Okay, the 0 to 1 transition where the reset signal is being generated should become very fast. But 1 to 0 doesn't have to be so fast, because already we have taken care of the emergency, and slowly we can make it from 1 to 0. So in this case, we will design the gate to be a high skew gate. What is the meaning of high skew? We are favoring the high transition, that is 0 to 1 transition, with respect to the low transition. Sorry. Sorry. So there we can do something to improve the performance of the gate, because the quality of the gate only depends on the low to high transition. Nobody is going to judge the gate based on the high to low transition. So that is an example of a high skew gate. Similarly, some other system, suppose the 1 to 0 transition is very important. Okay, in that case, we can design the gate to be a low skew gate. That is, we can design the gate to favor the low transition. And how do we do this? Okay, oh, we will not worry too much about the GUGD. We are of course going to look at that. But before that, let me say the rules for the sizing. Okay, how do we first set the sizes for the transitions? And the way to do that is, you decide, you have a gate, right? Take a two input NAND gate. A two input NAND gate, we can go for high skew or low skew. Now, if it is a high skew gate, then what you have to do for the pull up network? Why pull up network? Because the high transition happens through the pull up network. So what you do to the pull up network is you make the sizes of the pull up network same as that of a unit inverter. That is, the pull up network will have size to the full network. Okay, and the low skew case, suppose you have a different gate, not the same gate. You cannot have a high skew and a low skew gate. You can either be a high skew gate or a low skew gate. So suppose now you have a low skew NOR gate. Now what you do is you make the pull down network. Why pull down network now? Because in NOR gate, in low skew, the transition is the high to low transition that happens to the pull down network. And there you make the pull down network similar to unit inverter, meaning similar to size 1. Okay, so this is simple. Now, how do you get the speed? You get the speed by making the non-critical network. Okay, what is the meaning of non-critical network? In high skew, the pull-up network is a critical network. The other network is the pull-down network, right? You make that network half the size. When you make something half the size of a regular size, you make it double the speed. That is the double the delay. Sorry, not double the speed, double the delay. And that is the penalty we are going to pay. We are going to increase the time for the non-critical transition, but like I said, nobody cares about that transition for these particular skewed gates. And by doing that, we will improve the logical effort somehow. Okay, so let's go back. Start with a inverter, low skew, high skew, and then we'll do step by step for all the gates. Let's go back to the whiteboard. Okay, let's start with the inverter. And okay, and 2 and 1. Now I will give high. Inverter circuit is the same. Okay, we cannot change the circuit as yet. We will change the circuit also in other families, but this is still a static CMOS inverter only. What did we say? For the high skew transition, you keep this same here. Okay, but this one is a don't care. Nobody cares about this. You don't have to keep this at 1. You make this half the size of a normal. That is what we do here. Okay, and this is the high skew, and similarly we can also do a low skew. So here what we do is this one, okay, you replicate that directly here. This you don't keep same as 2, you make it 1. This is the low skew version of a static CMOS inverter. Now how do we calculate the logical effort? Okay, so for logical effort, again we have this thing, we have a pull-up network. So I'll calculate the logical effort by drawing the equivalent inverter. Okay, equivalent inverter. In this case, the PMOS network has size 2, NMOS network will have size 1. So when calculating the logical effort, you will have input capacitance of this gate, that is 2 plus 1 by 2 divided by 2 plus 1, 3. So I'll erase this. So yeah, 2 plus 1 by 2 is comes up to about 5 by 2 by 3. So 5 by 2, the whole by input capacitance of equivalent inverter for this transition. So that is 3 equal to, okay. Now for this transition, suppose this has become better, right? Because for an inverter, the logical effort is 1. For this particular inverter, the logical effort of the low to high transition is 5 by 6, which is better than that of inverter. But if you calculate the GD, okay, that is going to be equal to, again, input capacitance of my gate is still 5 by 2, but now is the difference. What is the equivalent inverter for the falling transition? Equivalent falling transition, the NMOS transistor has size 1 by 2, which means if I make a unskewed or symmetric inverter of size 1 by 2, okay, this cannot be 2 because I have to maintain the 2:1 ratio, right? Which means this will become 1. This is the unskewed inverter for the falling transition, which means the input capacitance of this inverter is 1 plus 1 by 2 is just 3 by 2, and this will give me 5 by 3. So this is where we see the trade-off. Nothing is free. Okay, we have made the rising transition better than ordinary inverter. The inverter will have logical effort 1. 5 by 6 is better than 1 because it is lesser than 1. But what has become worse? The falling transition is become 5 by 3. But nobody cares about this. This is not going to happen so often. This is the one that is going to be more important. Okay, and the same thing you can do here. So using the same arguments, G D, in this case we will do GD first, equal to 1 plus 1 is 2, okay, divided by 1, 1. So here I will go back to 1 and 1. So 1, so I put 1 and this become 2 because it's a symmetric inverter, and automatically the input capacitance of that is 3. So this has become better. But what has become worse for this inverter, if you calculate the logical effort for the rising transition, you have to size the equivalent inverter similar to this. So this is going to be 2 divided by, now change the sizes here. What is to put this one, sorry, this is a bubble. I forgot to add the bubble everywhere. Okay, so this is 1. If this is 1, this is symmetric inverter, this is 1 by 2, which means 2 divided by 3 by 2 equal to 4 by 3. So it has become worse for the rising transition for this inverter, but this is a low skew inverter. Nobody cares about the rising transition. This is the trade-off. But what we have done is we have improved the rising transition for the high skew inverter better than a normal inverter. We have improved the falling transition for the low skew inverter better than a normal inverter. So this is the goal of the skewed gates. One particular transition, you improve it at the cost of the other transition. So let us look at another 2 input gate. We'll start with a 2 input NOR gate. So the first set of sizes is just the normal sizes. So 1, 1. This is 4 and 4. Okay, so let us do the high skew over here. So it is a high skew. So PMOS transistor network, I will not change any of the sizes. I'll put the same sizes. NMOS transistor, I will make the sizes of all the transistors half. Put the ground here. 4, 4. Repeat here also 4, 4. Here 1, 1, I don't need that much size. I don't care about the transition. So I make it 1 by 2, 1 by 2. So therefore, G U equal to, now this is a 2 input NOR gate. 2 input NOR gate, if you remember, logical effort is 5 by 3. So whatever you calculate for the high skew, it should be lesser than 5 by 3. So how much is it? Take the gate. This is the input. It's connected to 1 PMOS, 1 NMOS. So it is 4 plus 1 by 2. That is, how much is that? 2, 4, 2s are 8. 9 by 2 divided by, now this is 4. So if you convert this into 1 PMOS, it is size 2 and the NMOS will be 1. So that is just 3. So this is equal to 9 by 9 by 6, 9 by 6 or 3 by 2. So we have improved. 3 by 2 is 1.5, 5 by 3 is 1.66. So our logical effort is lesser, which means that this gate is going to be better than an ordinary gate. But what is the cost? GD equal to, what is the numerator? Same, 4 plus 1 by 2 only, 9 by 2. What is the denominator? Okay, now look at this network. This is my pull down network. It is half, which means if I make this into a single inverter symmetric, it will be half and that will be 1. So 1 plus 1 by 2 is 3 by 2. So it has become 9 by 3. It will become obviously much worse. So 9 by 3 is 3, right? But that is the nature. You cannot get a free improvement. You are going to improve it at some cost. And we're improving the rising transition at the cost of the falling transition. Similarly, we can do a low skew version also. Repeat, don't change anything. Okay, 1, 1. Here, 4, 4 is too much. I don't need so much. I'll put only 2, 2. So GU should be lesser than 5 by 3. How much is it? 1 plus 2 is 3. So 3 divided by 3. Very nice. Reduced from 1.666 to just 1. What happened to GD? Same, 3 divided by, now this is 2 and 2. So together this is a NMOS two PMOS transistors, 2 plus 2, their size is 1. Okay, so 1 means this will be 1 by 2. So 1 plus 1 by 2 is 3 by 2. So this goes from 5 by 3 to 6 by 3. So it has become worse, but this is the one that is more important. It has become much better. Here also this is the one that is more important. It has improved, and this is the idea behind skewed gates. We can, if there are some special cases where one particular transition is better, then we can improve the performance of the gate for that transition. The other transition has become worse, but we don't care because that transition happens very rarely, or that transition has more time to perform the operation, etc. Okay, so next we will continue with the ratioed circuits. Okay, so we'll stop this now.